Nobody is going to warn you. There will be no emergency broadcast, no countdown on television, no president standing at a podium telling you to stay calm, because by the time anyone on Earth realizes what is coming, it will already be too late to do anything about it. Right now, as you watch this, astronomers have confirmed something that was once dismissed as science fiction. Runaway black. Holes are real. They tear through galaxies. They travel at millions of miles per hour. And the universe's own physics makes it impossible to detect one heading toward us until its gravity has already begun dismantling our solar system. This is not a theory. This is happening. Somewhere out there, the clock has already started. There is a question that physicists have quietly discussed in university offices and late-night conference rooms for decades, and it is a question that nobody in mainstream media has had the courage to take seriously. What happens to Earth if a black hole passes close by at extreme speed? Not a collision, not a direct hit, just a passing visit. Because here I ask the part that nobody tells you, you do not need to fall into a black hole for it to end everything. You just need it to get close enough. And in early 2025, the James Webb Space Telescope confirmed something that changed the conversation permanently. Runaway black holes are not theoretical constructs. They are real, they are moving, and at least one of them, a gravitational monster weighing 10 million times the mass of our sun, has been observed rocketing through space at 2.2 million miles per hour. That is 3,000 times the speed of sound. And that is not even close to the speed of light. Think about what that means. A black hole moving at the speed of light would be traveling at 670 million miles per hour. It would cross the distance between Earth and the Moon in less than 1.5 seconds. If something like that passed through our solar system, the gravitational consequences would not unfold over days or weeks. They would hit us in a sequence so compressed, so violently accelerated, that the entire process from first gravitational disturbance to complete planetary destruction would happen before most human beings even had time to understand what they were experiencing. This is the scenario that physics actually predicts, not Hollywood, not science fiction, actual peer-reviewed, mathematically derived physics. But here is where it gets more complicated and more dangerous than you think. To understand what a near light speed black hole does to Earth, you first need to understand what a black hole actually is. Not the simplified version you learned in school, but the real physics underneath it. A black hole is not a vacuum cleaner. It does not suck things in from across the universe. It is a region of space-time where gravity has become so extreme that the escape velocity exceeds the speed of light. Nothing, not matter, not radiation, not information of any kind, can escape once it crosses the event horizon, the invisible boundary that marks the point of no return for a stellar mass black hole, the kind formed when a massive star collapses at the end of its life. That event horizon might be only a few kilometers across. But the gravitational influence extends far beyond it. The real weapon of a black hole is not its event horizon. It is what physicists call the tidal force, the differential in gravitational pull between the near side and the far side of any object that gets close enough to feel it. Here is what that actually means for you, for Earth, for everything you know. The moon's gravity pulls on Earth, and the difference between the gravitational force on the side of Earth facing the moon and the side facing away from the moon creates the tides you see every day. That difference amounts to a fraction of Earth's own surface gravity, and it gives us tidal patterns that have governed human civilization since the first sailors learned to read the ocean. Now imagine replacing the moon with a stellar mass black hole. Imagine the gravitational differential is not a fraction of surface gravity, but millions of times stronger. The near side of Earth would be pulled toward the black hole with an acceleration so catastrophically greater than what the far side experiences that the entire planet would begin to stretch. Not metaphorically, literally. Earth's solid rock, its iron core, its oceans, everything would begin to elongate in the direction of the black hole. Scientists call this process spaghettification. It is a casual name for the most violent thing that can happen to a physical object. And here is where the speed becomes the most terrifying variable in the entire equation. At normal astronomical speeds, a black hole passing through a solar system would exert its gravitational influence over an extended period. The planets would feel the pull, orbits would destabilize, and the chaos would unfold across thousands or millions of years. The outer planets would be the first to respond, their orbits bending, elongating, or breaking entirely as the black hole's gravity rewrote the gravitational landscape of the solar system. Neptune would go first, its distant orbit the most vulnerable to the gravitational disturbance, then Uranus, then Saturn, then Jupiter. Each planet either flung out into the cold void of interstellar space or dragged into a chaotic new trajectory that would eventually intersect with another body. The cascade would take time, but the outcome would be inevitable, a solar system reorganized or destroyed by gravitational chaos. But at the speed of light, none of that slow cascade happens. At the speed of light, the encounter would be compressed into a duration so brief that classical descriptions of it barely apply. This is the part where the physics becomes genuinely disturbing. According to Einstein's special theory of relativity, an object moving at the speed of light, if such a thing were, possible for a massive object, and we will get to why that matters, would experience a complete halt of its own time. From its own frame of reference, no time passes. The journey is instantaneous. But for the observers it passes, the experience is something else entirely. The gravitational field of such an object would not arrive gradually from a distance. It would be compressed, intensified, and hit with almost no warning. The gravitational distortion would be so concentrated along the direction of travel that it would arrive like a shock wave, and it would depart just as suddenly. What most people are not seeing is this. The brevity of the encounter does not reduce its violence. It concentrates it. Imagine the ocean floor suddenly rising by a kilometer and then immediately dropping back. The damage is not caused by the sustained presence of the elevated floor. The damage is caused by the shock wave that the sudden movement creates. A black hole passing at near light speed through the inner solar system would create a gravitational shock wave, a ripple through the very fabric of space-time, that would hit every body in its vicinity with an impulse of gravitational force compressed into milliseconds. Earth's crust would respond, the mantle would respond, the core would respond. Every layer of the planet experiencing a sudden violent pull in one direction, followed almost immediately by that pull's withdrawal, would mean that Earth would ring like a bell struck by a hammer that no engineer ever imagined building. According to informed sources in the astrophysics community, the seismic consequence alone would be apocalyptic. Every fault line on the planet would activate simultaneously. Every dormant volcano would receive the pressure impulse needed to erupt. The energy involved in such a gravitational shock wave would dwarf every nuclear weapon ever built, every earthquake ever recorded, every volcanic eruption in human history. And that is only the ground. The oceans would behave like water in a glass that someone has suddenly yanked to one side. The gravitational pull of the passing black hole, even at the extreme speed that makes the encounter brief, would draw the water on the near side of Earth toward it, creating a tidal bulge of truly prehistoric proportions. And then, as the black hole passed and the gravitational influence shifted and withdrew, that water would collapse back in the other direction. The result would be mega tsunamis of a scale that geological records on Earth have no precedent for. Not the 100-meter waves of the asteroid impact that ended the Cretaceous period. We are talking about walls of water potentially kilometers high, moving across every ocean on the planet at the speed of sound through water, which is roughly 5 times faster than it moves through air. Every coastline, every port, every coastal city that houses the majority of the world's population, gone. But even that is not the deepest layer of destruction, and this is where everything changes. Earth has a magnetic field generated by the movement of liquid iron in its outer core. That magnetic field is not just a curiosity of geophysics. It is the shield that stands between Earth's atmosphere and the constant particle radiation streaming out of the sun. The solar wind, a continuous flow of charged particles ejected from the sun at speeds of a few hundred kilometers per second, would strip away Earth's atmosphere over geological time if the magnetic field were not there to deflect it. Mars lost its magnetic field billions of years ago, and Mars lost most of its atmosphere. That is not a coincidence. It is cause and effect written in planetary geology. The gravitational shock wave of a passing near-light speed black hole would not just shake the solid Earth, it would disrupt the fluid dynamics of the outer core. It would disrupt the convection currents that generate the magnetic field. And if that field collapses, even temporarily, even for a century, Earth's atmosphere begins to bleed away into space at a rate that makes recovery an open question. The real story is that we could survive the physical shockwave and still face a slow-motion atmospheric extinction that plays out over the following centuries. But here is the layer of the problem that the mainstream conversation never reaches. We would not see it coming. This is not a rhetorical device. This is a statement of cold physics. A black hole is, by definition, invisible. It emits no light. A stellar mass black hole moving through the intergalactic void between star systems has no surrounding. Accretion disk, no jets of high-energy particles, no luminous material being drawn into it that would give off the X-ray signals that allow astronomers to detect black holes near other stars. It is darkness traveling through darkness. And at the speed of light, the event horizon of our instruments would arrive at the same moment as the gravitational shock wave itself. By the time we detected it, it would already be passing through the outer solar system. In 2025, Yale astronomer Peter Van Dokkum led a team that published observations from the James Webb Space Telescope showing a contrail of newly forming stars stretching 200,000 light-years across a distant galaxy. That contrail was the gravitational wake of a runaway black hole 10 million times the mass of the Sun, moving at close to 1,000 kilometers per second. The black hole itself was invisible. Only its consequences were visible, stars forming in its gravitational wake the way foam forms in the wake of a ship. A separate observation confirmed another runaway in the galaxy NGC 3627, this one approximately 2 million solar masses, leaving a contrail 25,000 light-years long. And if these supermassive runaways exist, confirmed now by multiple independent observations, then the laws of physics demand that smaller stellar mass black holes, the kind formed by ordinary supernovas in ordinary galaxies, must also exist as runaways. Smaller, faster, and completely undetectable until they are catastrophically close. Read that again. Completely undetectable until catastrophically close. The mechanism that produces these runaways is not exotic. It is fundamental. When two black holes merge, an event now confirmed hundreds of times over by gravitational wave detectors like LIGO and Virgo, the merger does not always produce a perfectly symmetric gravitational wave emission. If the two merging black holes have misaligned spins, the gravitational waves they emit during the final moments of the merger are stronger in one direction than in others. The merged black hole recoils from this asymmetric emission the way a cannon recoils from firing a shell. Physicists call this the gravitational wave kick. The velocity imparted by this kick can range from a few kilometers per second to thousands of kilometers per second, depending on the mass ratio and spin configurations of the merging pair. At the extreme end, a kicked black hole can be ejected from its host galaxy entirely, launched into the intergalactic void at speeds that dwarf anything else in the observable universe. These are the rogues, the fugitives of the cosmos. And in 2025, for the first time, astronomers confirmed with observatory-grade evidence that they are real. And what most people are not seeing is the implication that follows directly from this confirmation. If they are real at galactic scales, the physics that produces them operates at every scale. A stellar mass black hole produced by a supernova in a binary system, or kicked by a merger of smaller black holes, can reach escape velocity from its home star cluster and drift into the intergalactic medium. There it travels invisibly, subject to no friction, losing no speed over time in the near-perfect vacuum of interstellar space. A black hole launched billions of years ago at the far side of our own galaxy could, in principle, be traveling toward the solar system right now, and there is no instrument currently in operation that would detect it in time to matter. The nearest known black hole to Earth is Gaia BH1, discovered in 2022 at a distance of roughly 1,500 light-years, a stationary stellar mass black hole in a stable orbit. Not a threat. But Gaia BH1's discovery was significant not because it was dangerous, but because it demonstrated something the scientific community had long suspected. These objects are far more numerous in our galactic neighborhood than anyone had previously confirmed. We had simply lacked the tools to see them, and here is where the scenario becomes truly unsettling at a human scale. The speed of light as a travel velocity for a massive object is, according to our current understanding of special relativity, physically impossible. An object with mass requires infinite energy to reach the speed of light. As it approaches that speed, its relativistic mass increases, and the energy required to accelerate it further approaches infinity. The speed of light is a universal speed limit that no object with mass can reach. This is settled physics. This is the framework inside which every particle accelerator, every satellite, every GPS system on the planet operates. We know it works, but the scenario of a black hole moving at a significant fraction of the speed of light, say 95 or 98%, is not prohibited. And at those speeds, the relativistic effects begin to manifest in ways that make the encounter even more violent than simple gravitational mechanics would suggest. At near light velocities, the black hole's gravitational field undergoes relativistic beaming. The gravitational influence is not distributed evenly in all directions. It is compressed in the direction of travel and reduced in the perpendicular directions. What this means is that as the black hole approaches, the gravitational force building in the direction of its path would be even more intense than Newtonian mechanics would predict. The shock wave ahead of it would be more concentrated, more sudden, more devastating. And in the wake behind it, the gravitational field drops off with an equal abruptness. The planet experiences not just a powerful gravitational pull, but a violent gravitational snap. The pull and release so sudden that the structural integrity of the planet itself is challenged in a way that no geological process in Earth's history has ever approximated. According to informed sources in the theoretical physics community, the exact sequence of destruction depends heavily on the mass of the black hole it's closest, approach distance, and its velocity vector relative to Earth's orbit. A stellar mass black hole of 10 to 20 solar masses passing within a few million kilometers, roughly the distance of the moon's orbit scaled up slightly, at near light speed would produce consequences, ranging from catastrophic to civilizationally terminal. A supermassive object at those speeds would produce consequences that end the discussion of Earth as a habitable planet entirely and permanently. But here is where it gets worse, and this is the layer that almost nobody talks about. Even if the black hole passed without directly shattering Earth's crust, without triggering the mega tsunamis, without collapsing the magnetic field, even in the most optimistic scenario where Earth physically survives the encounter, the gravitational perturbation to the solar system would not be over. The orbits of every planet, every moon, every asteroid in the solar system would have been altered by the passing gravitational field. The delicate gravitational balance that keeps Earth in its stable, nearly circular orbit at just the right distance from the Sun, the balance that has maintained our climate within habitable ranges for billions of years, would be disturbed. Even a small perturbation in Earth's orbital parameters can produce significant climate effects over centuries and millennia. An orbital shift that moved Earth 5% closer to the Sun or 5% farther away would initiate a runaway greenhouse effect or a snowball Earth scenario, respectively. Life might survive in some form in some places, but the civilization that built cities and wrote poetry and launched telescopes into space to find the very black holes that destroyed it, that civilization would be gone. The real story is not what a black hole does to a planet in the moment of closest approach. The real story is what it leaves behind. The James Webb Space Telescope has given astronomers a view of the universe's violence that no previous instrument could provide. The contrails of star formation, stretching hundreds of thousands of light years behind runaway black holes, are not just beautiful astronomical photographs. They are evidence of a cosmic mechanism, merging black holes generating gravitational wave kicks, ejecting remnants at speeds that can cross intergalactic distances, that is woven into the structure of the universe at every scale. The universe is not static. It is not orderly in the way that the comfortable science communication of previous generations suggested. It is populated with invisible, high-speed gravitational anomalies traveling through the voids between galaxies, and by extension through the voids between stars, and by extension through the neighborhoods of planetary systems exactly like our own. The uncomfortable truth that emerges from the 2025 observational data is not that this will happen to Earth. The probability of any such encounter within the next several billion years is, by honest calculation, minuscule. What the data reveals is something philosophically more challenging. The universe contains categories of threat for which we have no early warning system, no mitigation strategy, and no meaningful response. For every threat that humanity has conceptualized and worked to address, asteroid impacts, pandemic disease, nuclear conflict, climate change, there exists a corresponding engineering problem, a response framework, a timeline within which human intelligence and collective action can theoretically make a difference. A runaway black hole at near light speed is not that kind of problem. It is a category of cosmic event that arrives faster than warning systems can operate and carries more energy than any human technology could deflect or absorb. It is the universe's reminder that for all the power of our civilization, for all the reach of our telescopes and the precision of our instruments, there are forces operating on scales and at speeds that place us permanently and completely outside the conversation about our own survival. That should change how you think about everything. It should change how you think about the fragility of the conditions that make life possible. It should change how you think about the assumptions buried inside every long-term plan humanity makes. And it should change how you think about the universe itself, not as a backdrop to human history, but as an active, dynamic, and different environment in which stability is not the rule, but a temporary and local exception. The black hole confirmed by James Webb in 2025, the one moving at 2.2 million miles per hour with its 200,000 light-year contrail of newborn stars, is not heading toward us. It is in a distant galaxy, a cosmological curiosity. But it is proof of concept. It is the universe showing its hand. And what it showed us is that the cosmos is full of invisible fugitives moving at speeds that collapse the distance between safe and catastrophic to a matter of milliseconds. In 2026, gravitational wave observatories are detecting merger events at rates that would have seemed impossible a decade ago. Each merger is a potential kick. Each kick is a potential runaway. And somewhere in the vast darkness between galaxies, between star systems, between the spaces we cannot yet see, with the instruments we have built, there are black holes in motion that no catalog has yet captured. Nobody knows how many. Nobody knows where they are. Nobody knows which direction they are traveling. And nobody, despite the satellites, the observatories, the supercomputers, the decades of scientific progress, has yet built the instrument that would tell us one was coming, before the gravitational shock wave arrived to tell us itself. So the question is not whether the physics allows for a black hole to pass near Earth at devastating speed. The physics does. The question is not whether runaway black holes exist. They do. The question is not even whether one could reach our solar system. It could. The question is this: what does it mean to live in a universe where the most catastrophic event imaginable can arrive with no warning from any direction at any time, and where the very nature of the threat makes preparation meaningless, That question has no comfortable answer, and the universe, as it turns out, was never designed to give you one.